أهلا وسهلا فيكم بجلسة الكيمياء لليوم. أنا كتير متحمسة إنه نبلش سوا هالمشوار العلمي الممتع. في هذا الفيديو سنتعرف على خصائص الأحماض الكربوكسيلية ومشتقاتها وتسمياتها وصفاتها والتفاعلات الكيميائية التي تقوم بها. خلونا نستكشف الكيمياء المدهشة عن الأحماض الكربوكسيلية والإسترات.
Welcome! Today, we are diving deep into the scent of chemistry. We're going to pull back the curtain and see exactly how one of the most important fragrance molecules, an ester, is made step by step. So, have you ever really thought about what gives a pineapple that sharp tropical smell? Or what makes a banana smell, well, like a banana? It's not magic. It's all chemistry, and it comes down to one special type of molecule. Our journey to create these amazing scents starts right here with this specific arrangement of atoms. What you're looking at is a carboxylic acid group. This is one of our main building blocks, the very first piece of our puzzle. And the big answer to our question? It's a molecule called an ester. Esters are the compounds that are responsible for so many of the fruity smells and flavors that we all know and love. And today, we're actually going to cook one up from scratch. You know, every great creation starts with a good recipe, and chemistry is really no different. So first things first, we've got to gather our ingredients. For the specific ester we're making, we need two main things. First up is a carboxylic acid, in our case, ethanoic acid. And second, we need an alcohol. We're going to use butanol. Just think of these as the flour and sugar of our chemical cake. Okay, so besides our main ingredients, we need a couple of essential kitchen tools to help things along. We're going to add a few drops of sulfuric acid, which acts as our catalyst. You can think of it as a chemical matchmaker. And we'll throw in some pumice stones, just to make sure the whole mixture boils nice and smoothly. So what is a catalyst, really? Well, simply put, it's something that makes a reaction happen way, way faster. It's kind of like a coach hyping up the team from the sidelines. It helps the molecules get together and react, but it doesn't get used up in the process itself. It's a super important tool for any chemist. All right, all our ingredients are mixed together. Now it's time for the cooking process. This is where the real magic happens, and we're going to use a special technique called reflux heating. Now, reflux might sound a little complicated, but the idea behind it is actually brilliant. You boil your mixture, but you catch all the steam, cool it down so it turns back into a liquid, and then let it drip right back into the pot. It's basically like boiling something with a lid on, but way more efficient, so you lose absolutely nothing. Okay, so check out this setup. It all starts down at the bottom in that round bottom flask. We gently heat our mix of acid, alcohol, and our catalyst, and we bring the whole thing to a nice, steady boil. See that long glass tube attached to the top of the flask? That's a condenser. As the hot vapor rises up into it, it hits the cold inner walls, which have cool water flowing around them. This instantly cools the vapor, turns it back into liquid droplets, and they fall right back down into the flask to keep reacting. Pretty clever, right? So why go through all this trouble? Well, there are two huge reasons. First, the heat makes the reaction happen much, much faster than it would at room temperature. And second, it means we don't lose any of our expensive ingredients, or more importantly, the ester that we're trying so hard to make. It's all about speed and making sure nothing goes to waste. Okay, after about an hour of reflux, our reaction is pretty much done. But now we have a flask full of, well, a mix of stuff, not just our pure ester. So it's time to move on to the purification stage. Right, so what's in our flask? We've got the ester we want, sure, but we've also got some leftover acid and alcohol that didn't react, plus our sulfuric acid catalyst. The next big job is to carefully separate our final product from this chemical soup. To get our ester all by itself, we use this cool piece of glassware called a separating funnel. So we pour our mixture in, we add some water, and then we give it a really good shake. After that, we just let it sit for a minute. And just like oil and vinegar, the mixture settles out into two totally separate layers. So what's in these two layers? Well, the bottom layer is what we call the aqueous, or water-based layer. That's where all the leftovers go, the stuff that dissolves in water, like the extra acid, alcohol, and the catalyst. And the top layer? That's our prize. That's the organic layer, which contains our ester. It doesn't mix with water, and it's less dense, so it just floats right on top, ready for us to collect. So we made our ester, we've purified it, but what if we want to get more of it out of the same reaction? This is where chemists get really clever and use a sort of pro tip to boost the final amount we get. The secret to this pro tip is a fundamental rule in chemistry called Le Chatelier's principle. Basically, what it says is if you mess with a reaction that's in balance, the reaction will try to undo what you just did. It's a constant push and pull, a balancing act that we can actually use to our advantage. So, how do we use this principle to get more ester? We've got two main tricks. First, we can just dump in a whole lot of one of the starting ingredients. The reaction will see all that extra stuff and work harder to use it up, which pushes things forward and makes more of our product. The second trick is to remove one of the products as it's being made. If we take out the water, for instance, the reaction will try to make more water to replace it, and in doing so, it also makes more of our ester.
And that's really the big takeaway here. Chemistry isn't just about mixing things together and seeing what happens. By understanding these core principles, chemists can actually manipulate and control reactions to get them to make more of whatever they want. It's a strategic game of pushing and pulling the reaction in the direction you want it to go.
So this whole process, it's not just some obscure lab experiment. It's absolutely fundamental to making the artificial flavors in your food, the scents in perfumes, and even some kinds of plastics. It really makes you stop and wonder, what other everyday things are hiding this kind of clever chemistry right under our noses?